So we stopped the last lecture at this point, which is k nearest neighbors, and I've sort of expanded a little bit the content here and later, and I will be posting this online, of course, as soon as I've recorded this lecture. Uh, so there's just a few remaining things that I want to show you about this graph and about how you would go about analyzing it or sort of characterizing it. So the first one is the nearest neighbors. And so I have here on the left the definition. So remember that the average neighbor degree is essentially a measure of how connected your neighbors are. Okay, so I have put, because the return was a little, I didn't remember what the return value of the function was, so I've put it here for memory. The return value of the KNN function when you run it is first a vector with the value of the average nearest neighbor degree, and the other value is the distribution of the vertex degree, the average vertex degree in the graph. So as it says here, in that second return value, first element is the average nearest neighbor degree of the vertices that have degree 1, and so on and so forth. And so that value, so the nearest neighbors can be done in a non-oriented, non-directed version, and that's when you use this O here. Or it can be in terms of in or out degree. And so here, if we run things, we see, and that's going to be interesting because, well, one thing that you can think about. So if you remember when we were looking at degrees, I did not. Ah, yes, I plotted the degrees earlier. When we were looking at degrees, Winnipeg had the highest degree. What's the eccentricity? I will get there. Yes, that's the degree. So Winnipeg had the highest degree, Thompson had the second highest degree, and there were a lot of locations with much, much lower degree. And that means if I'm Winnipeg, for instance, then my average degree for my nearest neighbors is going to be quite small. Whereas if I'm a nearest neighbor of Winnipeg, then the average degree of my neighbors is higher. And this is what we are going to observe here. When I get there, if you look at the values, for example, Thompson and Winnipeg, which are the two vertices with the highest degree, the two nodes or vertices with the highest degree, they have some of the lowest, and actually the lowest nearest neighbor degree, because precisely of what I was explaining before. They are the dominating nodes, and so their nearest neighbors are less than them. And the opposite is true. The neighbors of Winnipeg or Thompson have the highest degree, and actually the places that are well connected to both Winnipeg and Thompson, such as this airport here, have very high nearest neighbor degree because they're connected to both, and these are two vertices that have high degree. Okay, and what I'm going to show you throughout the remaining of this, and I mean I've done it before, but I'll continue doing this, is how you can incorporate this in a plot because it is much easier to visualize things if you plot them usually. So I'm going to plot the k nearest neighbors. I chose here to illustrate things with the in degree. We could do the same way for out or no orientation. So here I'm going back to larger plots. I just say that the k nearest neighbors in degree are those in the Manitoba graph and I just already select that output. So that output is here, and I'm ignoring this distribution here. I just need the values for each of the vertices. I set them as well. I decide on this color bar, and then I set the values of the vertices to be the value of the color bar in these vertices. The value of the color bar for the values of the nearest neighbors for this. By the way, and then this is what I will plot, and often it's useful to round the results. And then I just plot, and this is what I get. So remember that Viridis is typically highest values are yellow, lowest values are purple. And yes, by the way, I've added this desk tool, the plural, to the list of packages that are being installed. So when you run the code, you will see this. It will, by the way, in passing, it will take some time to install. But where am I here? This way you get a nice little color bar on the side, which indicates what the values are. This is not a very convenient color bar because you can't really control how the numbers are laid out. We will see a problem with that later on, but it's illustrative. I mean, it's possible to do much nicer color bars, but this was an easy way to do things. And so, here, as I was saying, you see that the situation is somewhat reversed from what we saw in terms of degree. Winnipeg and Thompson have the lowest nearest neighbor degree, and it is the places that are connected to one or both of them. This is not showing much. That have the highest degree, the highest nearest neighbor degree. Sorry. Okay, now let's look at coreness. So remember that coreness, and let me skip over to that. Coreness in a graph is the number of neighbors you have, and it's the idea that you can create subgraphs in which each vertex is connected to a certain number of other vertices. So a one core would be all the vertices that are connected to at least one neighbor. A two core is all the vertices that are connected to at least two, and so on and so forth. And coreness is direction. It has a direction. So here I'm calling coreness with all, which is, again, remember what happens. All means I'm not considering the direction of the arcs. In coreness or out coreness, depending on whether I'm looking at in arrows pointing in or out of the vertices. And so if you look at these numbers, you see that, well, of course, when I don't consider orientation, the coreness is higher, because it just the degree becomes higher. It's considering two arcs, therefore the degree is 2 whenever there is a return here. But let's look at what did I do here? Out coreness. So if you look at out coreness, there's a certain number of vertices that have a coreness of 1. That means that they belong to the 1 core, but not to the 2 core. And coreness goes all the way to 4. Okay, so for Winnipeg, Thompson, and a couple of other airports, if I remember, YGO here, and I think there's a fourth one which I am not picking up. YGO, yes, YOH. Don't remember those codes. I should perhaps at one point just print them out. So again, we do as we just did for nearest neighbors. We are going to plot this to visualize a little bit. And so what I'm going to indicate here is the coreness of the vertex. So I just assign, not assign here, where is it? Yes, I'm assigning the color to be the color of the cores, which is what I've saved as being the coreness. Okay. And so here you see it, and I've put a little legend. I'm also, at the same time as I'm showing you these things, I'm also showing you how you can sort of make slightly nicer plots. These are not, this is not something I would put in a publication. I can make much, much nicer plots, but this is good enough as a sort of first approximation to show what is happening. So here I'm showing the coreness of the vertices. So that color is 1. Coreness has only 4 values, so I don't need to look at a range of values, just the discrete values. So Winnipeg, Thompson, and these, oh, there were 4. I'm looking at the out. I missed one. 1, 2, ZGI also has coreness 4. So these 4, this is the out degree, okay? The out coreness. So these 5 places form a subgraph. So they're all connected to one another. And that subgraph has degree out degree 4. So each one of those vertices in yellow are connected to 4 of the other vertices, because there's 5 here. They're connected to the 4 other vertices. The second degree of coreness, and of course, they're also, if they have K core, they have all the lower values of K cores. So if we look at the free core, it's the yellow and the green. Okay, so all the yellow and the green form part of the free core, and the same way all the blue, green, and yellow form part of the 2 core. Okay, but I'm just indicating, so you have to remember that I probably could plot all the colors in the vertices, but this is not something I'm going to waste time over. So just remember that things go down. So if you're part of 4, you're part of all the others. If you're part of 3, you're not part of 4, but you're part of all the others, and so on and so forth. So this gives you a good idea of the organization. So between those 5 places that are in the 4 core, for example, you can go anywhere. Between the places that are in the 3 core, so the yellow and the green, you can go to 3 of the others. Okay. Now let's look at betweenness. So if I look at betweenness of the graph itself and betweenness of Manitoba, you'll see that the betweenness of Winnipeg is the highest by far, and then Thompson, and then the rest of the world. This would be very different if we hadn't done this aggregation of the rest of the world as we did. You would see that if instead of aggregating all the rest of the world in one vertex, we had kept different vertices, we'd see that the betweenness of Winnipeg would be even higher, because it's connected to so many other different places. So most of the shortest paths coming in from the rest of the world into an airport in Manitoba go through Winnipeg. But because of this arbitrary thing that we did to the vertices outside of Manitoba to group them all together, this gives a sort of lower importance to Winnipeg than it should have. Okay, because remember, so if you're coming from anywhere that is any of the 4,000 minus a few other vertices in the graph, your inflow into the network is going to, into the Manitoba network, is going to be through that single vertex. And so that vertex is on many, many, many shortest paths. Okay, but given how we are looking at things, the centrality, the betweenness centrality of Winnipeg is not so different. I mean, it's a bit bigger, but not so different from that of Thompson. And then there's a few vertices that have zero betweenness. Okay, so these are peripheral vertices in terms of the graph. There is no shortest path that goes through them that does not involve them as a starting point or an end point. They are not in the shortest path between any other pair of airports except themselves. And the same way as we've done, I'll show you the result as a plot. And here I'll just point out that there was it took me a little while to figure this one out. Because there are vertices that have betweenness 0, you have to shift things by 1. Contrary to what we did before, where we could just say colbar of the values, here we have to add this +1 because colbar of a 0 entry is nothing. Vectors in R start positioning at 1, not at 0, like in other programming languages. And therefore this was failing. So if you have a value 0 in a vector and you want to do this operation here, remember to add a 1. Aside from this, it's very simple. So in this case, there aren't that many different values in practice. There's 0, there's some that are quite low, and there's 2 large values. And so this is what you're seeing here. You're not seeing much difference between 0 and very low because you're really down in the color bar here. And on the other hand, Thompson is somewhere around here, 260 if I recall, no, 211. And Winnipeg is the highest betweenness. And I'll finish with closeness. And closeness, I'm going to show you, is really interesting in the case of this graph. I actually would need a little bit more time to come up with a good explanation of what we're going to see. Although it's not too complicated, I should advance this. Betweenness, that's what we were using. Let's go to closeness. Okay. And okay, so let's look at closeness. Closeness is a directed function in iGraph, so we can compute the closeness without considering direction, with the in closeness or the out closeness, depending on what type, what direction we're following the arrows in. First of all, the way, if you recall, the way we've assigned the volume of passengers to the graph edges, arcs, was by, let me just show you quickly this, was by using, let's say GMB, but it's the same for the other one, was by using this, oh, I haven't run the, oh, no, it's not the vertices, it's the edges. Was by using that keyword vol, okay? Because in as I explained in the previous lecture, when we do this table that we made here, where was it? That vol here, volume, when we use this, where is that guy? Here. When we use graph from data frame, it takes the first entry to be the origin vertex, the second entry to be the destination vertex, so first column and second column, and all the subsequent columns are added as properties, essentially like that you would access with a dollar sign something, to this to the edges or arcs. And so what it's doing here is that okay, there's the volume. So if you have something called weight, then it is going to do the weighted version first. If this quantity is like it is here, no, because we haven't defined it, then what is done is that it's the geodesic distance that is used. Okay, so where the distance between two vertices is simply the number of jumps from a vertex to another, whether we're using this function or the other. So in iGraph, it's the second formula here, oops, the bottom one that is used, not the first one. Okay. So when you do this, well, you get those closeness measures. I'll just point out, so as I was just saying, you can also compute the weighted version. So if that list entry is not defined, that list entry weight is not defined, then what you need to use, you need to specify it. So you do it this way. So to do, I'm just going to save the results because I'm going to be manipulating them later. And I'm going to look at the weighted case. So the weighted case I get by specifying that the weights are whatever I want them to be. So again, so if weight is defined as an entry of the list properties for arcs, it will be used, but otherwise you just trigger it by doing this, something like this. Okay, whatever your column for weight was in your data frame. Okay, so this just says look at the closeness out and look at the closeness out, but this time the weighted version. And you're going to see this is going to be quite interesting because it's going to be quite different, whether we look at the closeness in terms of the weighted version or the unweighted version. So let's plot things. And so just before I start this, you know, like when you look at these values, they are not really, but that's where a plot is really important if you look at this, because this is not saying much. But if you look at the values, they look between 0.2 and 0.3 or whatever. So it's good to sort of get a sense of what is there. And for this, I'm going to look at the range of the values. So U is for unweighted here and W for weighted. Okay. So I'm going to look at the range of values and also what they look like. What type of distribution of values do I get? So the range for the unweighted is from 0.01 to 0.03, almost 0.04, almost 0.02 to almost 0.04. And here is from 2 to the -5 to 6 to the -5. And the values, they look like this for the unweighted case, and they're much more linear in the weighted case. but altogether there's going to be a nice spread of values, so the plots should be nice. What we want to do is we want to spread things so that we have at least 10 or more different values of the colors. And so what I'm going to do is I'm going to multiply this so that I go from, I don't remember if it's 196, yeah, probably 196 to 370. So that gives me about a 200 range of values, and try to do the same thing for this. So this is what I do here. I end up multiplying the range by 1 to the E4, so 10,000 for the unweighted case, and 1 to the E7 for the weighted case. And that gives me these ranges, which are quite nice. Okay, there's about 400 different values in the second one, of different possible values, and about 200 in the first one, so that's good. And so again, we do the same thing. So here I'm going to say that there's about, like, if you look at the first one, there's about 200 values. I don't want to start part way in my color bar, in my color map, and finish at the top. So what I'm doing is I'm looking at the width of an interval of values, so which is what I compute here. And then I make my color bar based on this width of range, not on from 0 to 370. Okay, but this means that when I'm computing the values, I have to subtract the minimum of the values from the original value. This way I'm shifting everything to the left towards the origin. But when I do so, of course, when I hit the minimum value, I have a value of 0, which means that I need to do what I just did in the previous case, 2 cases ago, I think. I need to add, no, actually the betweenness case. So I need to add 1, I need to shift things by 1, because otherwise things fail when we're doing this. Okay, so this is what this is doing. So when I plot this is the undirected case. Winnipeg has the highest closeness, so it is it is closer to the others. And Thompson comes second, and then things go down from there. And now let's I'm a little. No, it has a higher closeness, so it's further. Ooh, I have to check. Anyway, it's ranked the highest. This is ranked lower, and the lower closenesses are here. Okay. Now, if I look at the weighted case, the situation changes completely. So, well, not completely, but you can see that now Thompson and these 2 other places have gone higher than Winnipeg. Okay, so incorporating the volumes has completely changed the situation. And to see this better, let me show you how you would plot, how you can, there are other ways, of course, how you can plot the 2 graphs side by side. I'm going to use this little command here, par mf row. This allows you to plot in a matrix of plots. So here what I'm saying is I'm going to plot 1 row and 2 columns of plots. And so the first plot command that you issue is going to go in the 1-1 position, and the second one is going to go in the 1-2 position. Okay. And so I'm doing the same plots exactly as before. This is a case where you probably would be better off with making a function. I haven't made a function here, but in a practical case, if I wasn't doing things like this, I would make a function that plots whatever vector of values I give it, okay? But here, let's look at this. So here I have the two plots, the unweighted case, so the geodesic distance case, and the weighted case, where the travel volumes are incorporated. Okay. And part of the question then became, okay, so if I'm seeing this, does the fact that we have neglected the rest of the world, which has a very different connection to the rest of the graph, as I was just mentioning when we were discussing betweenness, does that play a role? So I'm going to do the same thing as before, but I'm going to throw in now also the graph with the rest of the world information. So I'm going to do the same, compute the the closeness, sorry, in the case that in the out degree case, and also in the unweighted case and the weighted case. When I look at the values that I obtained, they're very similar to the values that I had before. So the multiplicating factors that I used to expand the data are going to work. And here I'm just doing the same plot. Sorry. But this time I'm going to make 2 rows and 2 columns. Do the same multiplication of values as before. So the unweighted case I'm multiplying by e to the 1e4, and the weighted case 1e7. The first 2 plots that I already had, I throw in the 2 additional plots. I probably could make a larger figure. In a paper, you would play on the size of things. And you can see here, these are the 2 plots we already made. And these are the plots when I'm adding the rest of the world. And so it's interesting here, because if you look, I mean, it's not, the magnification is not great. Rest of the world has low closeness when we are considering, well, look, it's not a very high closeness when we are considering the unweighted case. But when we weight, we still have Winnipeg going down, Thompson going up, but now the rest of the world also goes up. As I said, I would have to think about it a bit more in order to give you a good explanation. This is not something I have looked at in this particular network yet. Actually, maybe give it a think. Look at the definition of closeness, look at the interpretation of closeness, and see if you can explain what we're observing here. And in terms of the assignment, that is asking you to sort of replicate this type of analysis. Whatever you end up choosing as your graph, perhaps these are interesting questions to ask as well. Is there something that changes a lot when you go from a weighted version of your graph, if you find one that is weighted, to an unweighted version, or do things remain the same? And that's these are sort of specific to the context and might change completely in other cases.